In this video, I want to do an example of how to calculate the inverse of a 3 by 3 matrix. So here we have the matrix M, and what we want to calculate is the inverse of M, which is equal to 1 over the determinant of M. And if that is notation you've not seen before, then this just means the determinant of M multiplied by a matrix here. And I write this matrix really nice and big, and I'm going to lay it out in a way that I think is helpful. So I suggest this is how you go about calculating your determinants. So what we're going to do, we're going to calculate something called a minor. And each element of the matrix M has a minor. So let's take the element 3 here. And the minor that corresponds to 3 is the determinant we get by crossing out all of these numbers in the row and crossing out all the numbers in the same column, and then taking the determinant of the 2 by 2 matrix, which is left. So our first minor here is 5 minus 1, 0, 0. Okay, to calculate our second minor, we do the same thing, which we take the second element in the top row, so minus 2. We cross out all the other elements in that row, we cross out all the other elements in that column, and we calculate the determinant of the remaining 2 by 2 matrix, which is 0, minus 1, 4, 0. Similarly, for the third minor we have here, so the third minor is what we get when we take the element 1 in the top row, cross out the elements in that row in that column, and take the 2 by 2 determinant of 0, 5, 4, 0. So then we keep doing this process on the next row. So if our next element is 0, here, we cross out the row and the column, and we take the 2 by 2 determinant of minus 2, 1, 0, 0. We do the same thing with 5. So we have the 2 by 2 determinant 3, 1, 4, 0. We do the same thing with negative 1, and we get the 2 by 2 determinant 3, minus 2, 4, 0. And then finally we do the same thing for the bottom row of the matrix. So the element 4, we have the 2 by 2 determinant minus what 2, 1, 5, minus 1. For the element 0, we have the 2 by 2 determinant 3, 1, 0, negative 1. And then finally, for the element 0, in the bottom right, we have the 2 by 2 determinant 3, minus 2, 0, 5. But that's not it, and there's two other really important steps we need to do here. So firstly, all of these 2 by 2 determinants are called minors. But what we actually want is something called a cofactor. And a cofactor is a signed minor. And we need to assign a sign, as in a plus or a minus, to each of these minors to make them a cofactor. And how we do that, we have the matrix of signs, which goes like this. And we just give the corresponding sign to each of those minors to make them cofactors. So we have a plus here, a minus here, a plus here, a minus here, a plus here, minus here, plus here, minus here, a plus here. So now these are no longer minors, these are now cofactors. And the other important step we need to do here is we need to transpose this matrix, and that just means switch the rows and the columns. And it doesn't matter when you do this, I like to do that right at the end, but we write this T here to tell us that at some point we know we are going to transpose the elements of this matrix. Okay, so let's continue with our calculation. And the first thing we probably want to do is we want to calculate the determinant of M. And as you should know, it doesn't really matter which row or column I expand this determinant by. So a sensible choice seems to be to expand it by the bottom row, because there are lots of zeros in there. So we're going to multiply lots of things by 0 and it makes our calculation a lot easier. So what do we know? Well, this is going to be 4 multiplied by the cofactor corresponding to 4. So we know that that cofactor is -2, 1, 5, -1. Notice that is just this cofactor here. And then -0 multiplied by this minor, so 3, 1, 0, -1, and then 0 multiplied by this cofactor, so 3, -2, 0, 5. And then calculating that, we know that both those second two are 0, so this is 4 lots of -2 times -1 is 2, subtract 5, so that is -12. Okay, if we then calculate all of our 2 by 2 determinants in here, what we are going to get is that M inverse is equal to 1/12 of, well, if we start calculating these, the first one we get 5 times 0, subtract -1 times 0, so that is just 0. In the next one we have -0 times 0, subtract -1 times 4, so that is +4, so times by -1 is -4. Here we have 0 times 0 is 0, subtract 4 times 5, so that is -20. On the next row we have -2 times 0, subtract 0 times 1, which is definitely still 0. Here we have 3 times 0, subtract 1 times 4, which is -4. And here we have 3 times 0, which is 0, subtract 4 times -2, which is +8, but then we have the negative here, so this is -8. -2 times -1 is 2, subtract 5 is -3. 3 times -1 is -3, subtract 0, but then we have a negative here, so this is -3, which is +3. And then finally here we have 3 times 5, which is 15, subtract 0, that is +15. And let's forget we still haven't transposed this, so we need our instruction to transpose. Okay, so the final step is to transpose this matrix, and we have completed our inverse matrix. So this just tells us to swap the rows and the columns. So my first row here is going to be my first column. So 0, -4, -20. And my second row is going to be my second column, 0, -4, -8. And then my third row is going to be my third column, -3, 3, 15. I've noticed a slight mistake here because notice our determinant was -12, so we need a -12 here. And finally, what you might do here is you might now take that factor of 12 inside the matrix and start simplifying those fractions. So we get 0, 0, +1/4, a third, 3 over -12 is -1/4, Negative 20 over negative 12 is 5/3. Negative 8 over negative 12 is 2/3. And then 15 over negative 12 is minus 5/4. And that is the inverse of our matrix M. Just for fun, I'd like to expand the idea of the inverse of a 3x3 matrix and try and find the inverse of a 4x4 matrix. So the process is going to be very, very similar. We have our 4x4 matrix A, and what we are going to do is we're going to take this first element 0 and cross out all the elements in that row and all the elements in that column, and we're going to find the determinant of this 3x3 matrix that remains. Then we will do the same thing for this second element. So negative 1, and we're missing a 0 there. So by crossing out all the elements in that row and that column, we're left with a 3x3 determinant of 3, 0, 2, 5, 1, 0, 0, 0, 2. Doing the third element, take the third element in that row, which is a 2, and cross out all the elements in the rows. We are left with a 3x3 determinant of 3, 0, 2, 5 minus 2, 0, 0, 0, 2. And taking the fourth element in that row and crossing out all the elements in the same row and column, we are left with a 3x3 determinant of 3, 0, 0, 5 minus 2, 1, 0, 0, 0. But again, we need to be very, very careful about the two important things we need to consider. So these minors, so these are minors at the moment, they need to be signs to make them cofactors. So our matrix of signs for a 4x4 looks like this. So we need to assign the correct signs to each of these. And now they are not minors, they are the cofactors. And we also need to remember we want to transpose this matrix. So you might want to pause the video here and you might want to try and complete all the missing cofactors in the remaining matrix A. Okay, and knowing that that would take a long time, I did that beforehand. So we have this matrix here and I've got all my minors, but we need to put in that important information of our signs. So we put in these signs here. And if you notice, when I made up this matrix, I tried to make our life a little bit easier. I put lots and lots of zeros in it to make these determinant calculations a bit easier. So I'm going to do the first row now. If we look carefully, it seems sensible to expand these determinants by the bottom row in each case. There's always a lot of zeros going on. So let's go ahead and do that. You might, if you want to do that yourself, pause the video now and try and calculate all of these determinants. But I'm going to do the first row. And as you can see, I've done a few of these already. So in this first row, what do we get? Well, we've got 0 times something, subtract 0 times something, add two lots of the remaining matrix here. So 0, 0, minus 2, 1. Zero, 0, minus 2, 1. If we do the next one by the bottom row, we get 0 times something, add 0 times something, and 2 times this matrix here. So two lots of 3, 0, 5, 1, but we need our sine of a -2. And then again here we have the matrix 2 lots of 3, 0, 5, -2. So 2 lots of 3, 0, 5, -2. And then finally this last element is nice and easy because all of these elements here are 0. This last element must be 0. And I've done all of these beforehand. I've left this last one here, this last bottom right element, just to notice that perhaps the easiest way to expand this determinant is by the middle row. And be careful about this, because if we're doing the determinant of 0, -1, 2, 3, 0, 0, and expanding that by the middle row, remember our matrix of signs for a 3 by 3 looks like this. So this is equal to -3 lots of -1, 2, -2, 1, plus 0 lots of 0, 2, 5, 1, subtract 0 lots of 0, -1, 5, -2. So what is that? Well, that is equal to 3 lots of -1, 2, -2, 1. So we have 3 lots of -1, 2, -2, 1. But it's really important that we have the correct sign. And sorry, that is not. That is -3. There's -3 here. So it is -3. So again, you might want to pause that and work out that matrix yourself. Okay, I have done that already, so you should end up with these elements here. And notice we still haven't transposed it, and we're still yet to calculate the determinant of A. If we think about what the determinant of A is going to be, the determinant of A is we can expand by any row and any column. So going back to A, it looks as if a sensible row to use would be this bottom one, because we can get 0 times something, add 0 times something, add 0 times something, plus 2 times the remaining elements here. So 0, -1, 2, 3, 0, 0, 5, -1, 2. And notice it is a +2, because if we go to our matrix of signs here, this 2 comes with the sign positive. Well, we don't need to worry too much about calculating this determinant, because we've actually already done it, because that is just going to be this element here. So actually we have calculated that element as being -9. So what is the determinant of A? Well, it's going to be the 2 that we had from before multiplied by -9. So 2 times -9. So finally, to complete our inverse matrix, we have A inverse equals 1/2 times -9 lots of, and now I'm going to do my transposition. So I'm going to transpose this matrix. So the first column is going to be 0, -6, -12, 0. Then the second column is going to be -6, -20, -10, 0, 0, 12, 6, 0, 6, 20, 10, -9. And just simplifying that, we end up getting an inverse matrix of 0, 1/3, 0, -1/3, 1/3, 10/9, -2/3, -10/9, 2/3, 5/9, -1/3, -5/9, 0, 0, 0 and a half. And that is our inverse matrix of A.